Hi, everyone. Thank you again for joining us for another session of JNation Online 2020. And here we have our sixth session of the day, as far as if I done my math correctly. So still a few to go. And I have the pleasure to have here with me Victor. Hi, Victor. How's it going?
Hi, how you doing today?
I'm okay. Thank you so much. It's a real pleasure to have you here with us, and thank you so much for joining us. So for today, going to talk us a little bit of Java concurrency or concurrent, right?
That's right, Java Concurrent Animated.
Yeah, I'm really looking forward to looking into this session. So without further delay, so please feel free to start.
Thank you very much. So I hope everybody's having fun at JNation this year. I feel bad that we can't be there actually in Portugal with everybody, but it's great that you guys
Yeah,
were able to put this
yeah. I
together.
mean, we had a lot of people that. I mean, you were scheduled to come as well, right?
Right.
To Portugal, and most of us are grounded. So this was the way that we figure out to do something anyway.
Well, I give
So
you guys a lot
hopefully,
of credit.
yeah. So hopefully, we're able to do it again physically next year. But I mean, nothing of this will be possible without people like you, Victor, and the other speakers that are still available to do this for us. So thank you so much.
Thank you, it's a pleasure. So let's get started. So in the early days of Java, all we had for concurrency were raw threads. And for inter-thread communication, we had the synchronized wait, notify keywords. And in fact, much of what we have today still uses those primitive mechanisms under the covers. But thread locking should be like visiting your mother-in-law. You do it fast and get out. And the components we have today help simplify that for a variety of common use cases. So what I've done is I've built a application called Java Concurrent Animated, and it depicts all of the components in the Java Concurrent API in Java. So before we do that, let's start with the synchronized keyword. This is the original mechanism for controlling access to resources that was provided in Java, and it's still available today. As I said, it's still the basis of much of what we do, but much of this is hidden behind the covers, but we still should get a fundamental understanding of how it works. So the way the program works is I'm always going to show like this big monolith in the middle, and that represents some kind of lock. In this case, it's going to represent a synchronized lock. On the right side, there will be snippets that illustrate how to use that construct in the code. And as we do things, you'll see that the snippets become highlighted. So in this case, let's start by adding a thread. The thread is hitting the synchronized keyword on sub-object, and it's doing some work, and you can see it's actively working. Thread is green. Green means it's in the runnable state. Threads have 5 states that they could be in. They could be at least 5 states. They could be starting, they could be runnable, they could be blocked, they could be waiting, or they can be terminated, or they can be timed waiting, which means kind of like waiting, except that they're going to expire. The wait will expire after a short time that you specify. So in this case, we see that the thread is green, and that means that it's in the runnable state, it's running. And now, let's say another thread comes in and tries to access that same synchronized block. So it hits the same synchronized keyword on the same object, and it can't get in. And we see that because it's blue, we see that it's in the blocked state. This is a great interview question. If a thread is waiting for a synchronized block, what state is it in? Is it in the wait state, the block state? So you see from here, the answer is blue blocked. Now, another thread will come, and again, it's blocked. It's trying to get into that synchronized block, and it cannot. When one thread exits the synchronized block, the thread scheduler will select another thread randomly to be in the runnable state. So let's exit, and we'll see. And it picked one at random. Now, just for your information, all of these components that I'm going to illustrate today are written as part of the Java Concurrent Animated application, are controlled by the exact component that we're illustrating. So in this case, these threads really under the covers are hitting synchronized blocks, and that is what's displaying as a result of the actual Java selection process. So you saw that it selected the second one, not the first. Let's add a few more. We see as we exit, it selects randomly another thread to run. And that's pretty much the basics of synchronizing. The idea is you need access, you need exclusive access to a resource. You add a thread, you go into the synchronized block, and now you're preventing any other thread from accessing that block until you exit. Now, how do you do inter-thread communication? You want to signal another thread to do some work. So let's say, for example, we are waiting for some state that doesn't exist yet, some kind of condition. So we want to wait until that condition is available, and we can't get it available until another thread provides that condition. So we go into the wait state, and we see that we became white. We called wait on the object, and we have to be in inside the synchronized block to call wait. So you see that the original thread that was running called wait. It turned white for wait, and it allowed another thread to get running. Now the other thread is working to complete the missing resource that was missing from this thread, the missing condition. And as soon as it's ready, it could call notify, which tells that thread that it is now, the condition is now fulfilled, and it should test again for the condition and finish performing its action. So this thread will now exit, and we see that another thread, since they were both in the blocked state, another thread is selected randomly to run. When that one exits, another one is selected randomly. In this case, there was only one. Now, one thing that's eye-opening, and again, this is a great interview question, and it's something important to realize is, let's say you have several threads that are in the wait state. What's the difference between notify and notify all? We know that only one thread can have access to the synchronized block. And right here we see an exception to that, because we see many threads are actually accessing that synchronized block. But the truth is that when a thread is in the wait state, it can occupy a synchronized block while another thread is running. And so all of these threads are in the wait state while this thread is running. That's the only exception, except for one other exception is they can be in the blocked state as well. So watch what happens here. When we call notify, the running thread calls notify on the synchronized object. See, it has to be in the synchronized state to call notify. It calls notify on the synchronized object, and the thread scheduler will select one waiting thread randomly to wake up. But it can't wake up yet because there's still a thread holding the lock. So what it does is it puts that thread into the blocked state, and as soon as I exit now, that blocked state will become runnable. So the top one is going to become runnable as soon as we exit the runnable thread. Now, what's the difference between notify and notify all? So we just called notify, and you see it wakes up one thread and it moves it into the block state. Notify all wakes up all of the waiting threads. And so now each one can test for its condition, and if that condition is fulfilled, it can continue working on that condition. And if the condition is not fulfilled, then it could go back to the wait. So let's exit. Thread scheduler picks a thread. We exit, we exit, we exit. And that's pretty much how synchronization works. One drawback to this is, let's say you have multiple conditions that you're needing to run. For example, let's say you need to know if something is below a certain level, and you also want to know if something is above a certain level, right? It's too hot in the room or it's too cold in the room. So those are two different conditions. So when we call wait, we're essentially saying that we're waiting for any condition. And once the wait is notified, it has to check for both of those conditions. So essentially, every waiting thread has to check for every condition that it needs to check for. What would be a lot sleeker is, imagine if we can make conditions unique, so that I could create a condition that says too cold, and I can create a condition that says too hot. Well, we can't do that with synchronize, but we can do that with a construct that was added later called the ReentrantLock. ReentrantLock works very similarly to the synchronized keyword, except you see over here that these are not blue, they're white. They're not blocked, they're waiting. And the nice thing about that is when you're in the synchronized block, let's just go back for that for a second. When you have block threads, there's essentially no way to stop any of these threads, except by calling the stop method, which is deprecated and considered a highly bad practice because it leaves a state in an unstable unstable state. But with ReentrantLock, what you could do is you could say lock interruptibly, and when you lock interruptibly, I am now able to interrupt any waiting thread. It'll throw an interrupted exception. So that's one benefit of using a reentrant lock instead of a regular synchronized lock. Another benefit is that you can create conditions. Let's reset that. You can create conditions on the fly. So I can have a cold condition and a hot condition. Let's say I want to create a new condition. So I say condition equals lock new condition. And that's creating a new condition. Now let's wait on that lock. So I'm waiting for that condition to come through. And now let's say I want to create a new condition. So I can call on the runnable thread, I could call condition equals lock new condition and create a new condition. That's the new too hot condition. Okay, and let's wait. So now we have one thread waiting for a cold notification, and it'll turn the thermostat up if it's too hot, if it's too cold. And I have another thread called the hot condition, and it'll turn the thermostat down if it's too hot. So now let's get in, another thread will now take the control. It'll get in the lock. And now it wants to notify that it's too cold in the room. So it'll signal condition 1, the cold condition, to run. And it'll exit. And now you see condition 1 ran. Okay, so it gives you more control over the specific conditions. So you can create more conditions and control them selectively. So that's a nice thing about the reentrant lock. One drawback of the reentrant lock is that you can only have access to the lock one at a time. But there is a construct called the semaphore, and that allows you to declare a number of locks that can be held concurrently. So in this case, we're going to create a semaphore that has 4 locks. You can provide access randomly by calling this constructor that just has the 4 in it over here, or you could provide a fair parameter that says select them, make a best effort to select the waiting threads fairly, meaning in the order that they arrived. So in this case, we're going to just do a regular one without declaring fair. And we are acquiring up to 4 locks. Now what happens after the 4th one is that waits. So remember, white is the waiting state, and therefore it's in the waiting state. Now you also have a try acquire, which means acquire it if you can. If you can't, just return false. You also have a time try acquire. So I'm trying to acquire it. I'll wait for 3 seconds and false. Now let's say I can now release one of the one of the waiting threads. Now I'm using all 4 of my permits. Now let's do a try acquire for 3 seconds. Okay, and I'll release fast, and you see the try acquire work that time. Okay, so that's the benefit of a semaphore, is that it's kind of like a lock, except that it allows you to declaratively specify how many concurrent threads you want to have accessing it at the same time. There's also an interesting use case is the ReadWriteLock. Let's say you have a situation where you have you need to be able to do occasional updates, and you have many readers going all through the day, but occasionally during the day you have updates coming, and you don't want the readers to read in the middle of an update. For example, I'm in the financial industry. Let's say we're trying to evaluate a portfolio, and somebody just bought 1,000 shares of IBM and they sold 1,000 shares of Microsoft. So their portfolio, if let's say we evaluated the value of that portfolio when they bought the 1,000 shares of IBM, but we did it just before they sold the Microsoft. So that portfolio is going to show it was too high, right? It's going to show that IBM and Microsoft are both in that portfolio when they really weren't. Really, we bought one and sold the other. So what we want to do is we want to be able to lock only when there are writers going on. But when there's no writers, we want to allow all the readers to access concurrently. And if there are any readers accessing the lock, we don't want to allow any writers in until the readers are done. So that's the purpose of the read-write-lock. The way it works is we create a read-write-lock. It's reentrant. The implementation, ReadWriteLock is an interface, but the implementation reentrant read-write-lock is reentrant. So it works just like a synchronized lock, meaning if you already have the lock, the same thread can acquire that lock again, but no other thread can. So let's see how it works. The first thing we do is we call read-write-lock, read lock, and then we lock that. Now another reader comes in. It is allowed to get that lock because readers can access the lock concurrently. But here's the hitch, a write lock. Now a writer comes in, it's the end of the day, it wants to update all the pricing from the end of the day market. It comes in and it can't get access to the read-write lock because the readers all have them. So now we'll unlock the readers. And finally, when there are no readers left, the read lock has access. Now, what happens if a reader tries to get access while the write lock is working? That should not work because we don't want any readers to come in. It might produce an inconsistent state. But once the write lock is done, we see all of the readers are able to get in. Now, I have a test question for everybody. Let's say we have a bunch of readers and a writer is waiting. And now let's say another reader comes. Should the thread scheduler allow him to get in or should he not? I mean, I can make arguments for both sides. If we allow him to get in, I mean, why prevent him from getting in? There are already readers there. On the other hand, maybe there's a reason not to let him in, and that's in fact is the case because remember we use a read-write-lock in a situation where there are many readers and rarely writers. So if we allow the reader to get in just because there are other readers there, the writer may never have a chance to run. So whenever we have a writer waiting, the read lock will wait too until the write lock is done. So we'll create a bunch of readers. We'll unlock the read locks. Now the write lock gets in. We'll unlock the write lock, and then all the readers can get in. So now that's the basic function of the read-write-lock. One thing you can do with a read-write-lock that's kind of interesting is, let's say you have a write lock, and you have a bunch of readers waiting. Now that write lock, since this is a reentrant lock, can do something pretty subtle. It can convert itself to a read lock. How? It can convert itself to a read lock by first locking on the read lock because it's reentrant, and then it can unlock the write lock. So let's actually do that. We'll call that the downgrade to read operation. And you see it became a reader now, and it allowed all the other readers in. Now, one caveat to that is you cannot upgrade a lock. So if you have a read lock and you try to upgrade it to a write lock, even though it's reentrant, we're not allowed to do that. Not using a read-write lock. There is, however, something that was added later, and that's called a stamped lock. Stamped lock is almost identical to a read-write lock. It has read locks, it has write locks. If you unlock, you get the write lock gets access. So it pretty much works exactly the same way. However, there's some more functionality that is applied to the stamped lock that you don't have in the read-write lock. First of all, it's much faster, so it's a good selection. The other thing is that you have this concept of an optimistic read. So you can create readers, and even though they are readers, where a read-write lock would normally block a write lock, in this case, it allows the write lock to come in. But if there's a write lock, you have to call the validate method on the read lock, the optimistic read, and the validate method will notice that it's invalid because of there's a writer in there. What you can do though over here, and I haven't implemented that yet, is you can convert a read lock to a write lock using a stamped lock. Okay, so you can upgrade them. So that's one benefit that the stamped lock has, besides just being faster. It's one benefit it has over the read-write lock. So those are the various kinds of locks that we have in Java, and the read-write lock and the stamped lock are really essential for many use cases where we need to prevent reading and writing from occurring at the same time. Next, we have executors. Now, in the olden days, when we wanted to create a thread, there were two ways to do it. You could create a thread and pass in a runnable and call start, or you could just attach a runnable to a thread and call start. Now we have the concept of executors. So in an executor, the way we do it is we have several different kinds of executors. I haven't implemented all of them yet, but the most common one is a fixed thread pool executor. And so we'll create an executor that allows up to 4 threads. And when you have an executor, you can call the execute method, or you can call the submit method. The difference is they'll both get to work immediately. The execute method will will exit when done, and the submit method will return a future so that you can get a result from it. Now, the pooled threads, you'll notice that as soon as one is done, it puts it back into the pool. So there is a certain amount of latency involved in creating a thread. And so there's a benefit to pooling the threads so that you can reuse them, so you don't have to actually recreate a thread. So that saves a little bit. You can also pre-start all of your core threads. So in this case, we had 4 core threads. One of them is being used, but it pre-starts all of them. And then when this is done, you'll see all of them are in the pool. So this is a new way. This is the way that we, instead of using threads directly, we can create executors. And this gives us more control over our application. When you do a new thread and pass in a runnable, you're just creating threads, and there's no limit to the number of threads you can create. Whereas with executors, you could throttle and control how many threads are being created concurrently, so that you don't overload the system by creating too many threads. There's also a saturation policy you can create, where if you create an executor, you can pass in a saturation policy. In this case, we have a rejected execution handler. So in this case, we have 4 threads. Once the 4 threads are exhausted, if a new thread comes in, it'll be rejected. And there are different saturation policies that you could use. You could have a rejection one like we did. You can have caller runs, so that the actual calling thread will run that thread. You can have a discard, so it'll discard the thread that's coming in, or you could have discard oldest. So if you have a bunch of threads waiting, it'll discard the oldest one. So you can make a choice of those. Okay, now there are certain specific kinds of blocks that are working for very specific use cases. In the case of a cyclic barrier, sometimes you want to prevent threads from proceeding until all threads are ready. One example I could think of is, let's say you need to scan websites for some keyword, and you only want to return a site if there are 4 pages on the site that contain the keyword. So you set off 4 threads and give each one a set of pages to scan. And as each thread finds the keyword, it calls the await method on the cyclic barrier. And if it fails, it'll call barrier reset, and then it starts again with the next site. So remember, we're always trying to find 4 matches. So 4 threads will come. Okay, I'm ready, I'm ready, I'm ready, I'm ready. Now we could all proceed, and we could report that that was a success. You can override the cyclic barrier and pass in a runnable method, and that will get called every time the barrier is hit one time. It'll get called one time. So we hit wait, wait, wait. Now the fourth thread says, oh, I couldn't find anything in my site. So that's a failure. So it has to reset the barrier and it will set all the other threads away. The runnable will never get called. And the cyclic barrier, cyclic because now it can be used again. It could always be used again. There's another similar concept, and that's called the countdown latch. And what the countdown latch does is you have, let's say you have, for example, you're starting up a service. And let's say there are some caches, 4 caches that need to be filled before you could start your service running. And you can't start processing until all the caches are ready. So what you do is all your processes will call await, and they're waiting for the caches to be complete. Now you have 4 caches. Each time a cache is ready, it calls countdown, 2, 3, and then as soon as the 4th one is called, it'll allow all of the processes to start running. So that's a particular use case where I think it's a common use case. For example, if you have a website and you need to have certain processes running or caches filled, and you can't start the website until all of those caches are filled. Now there's there's a component called the phaser that kind of combines all of that, and plus it adds more. So with the phaser, it works very, very similarly to the, let's use a case where we see that it's similar to the countdown latch. So we have a wait advance, and then we have an arrive method, and we need 4 of them. And once we arrive, we see it works exactly like the countdown latch. Okay, so we wait, and then we arrive, bang, 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 and it allows everything to go. It also works very similarly to the cyclic barrier. You have the arrive and await advance method, and you see it works just like the cyclic barrier. But the difference here is that you also have register methods. So you see I created this phaser with 4, but I could register additional permits. And now let's do arrive and await. And you see before where we were at 4, now we have 5 permits that are required to wait. We also have arrive and deregister. We could have bulk register, so I can add, let's say I want to add 2 more permits. Bang, 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 bang. Those are my 5. Now I have to add 2 more, and now that it lets them go. So it gives you a little bit more control so that you can decide dynamically during the execution of the program how many permits to allow, where countdown latch and cyclic barrier require that you declare those in the beginning. Excuse me. There's also a concept of a blocking queue. And what a blocking queue does is it's a producer-consumer pattern where threads could supply completed pieces of functionality asynchronously. And then you could have takers that will take from the blocking queue asynchronously. So the puts there, and you see the thread quickly ran away because it's done. It puts it and it leaves. Now I have a taker that could come and take from the queue, and it's calling the take method on the queue. Now, what happens if I exceed, in this case, I created the queue with 4, capacity of 4. So what happens if I exceed that capacity? So the thread that's trying to put that object on the blocking queue will, it will block. It's actually in the waiting state. It cannot get further until something else takes it away. Now there's also an offer method, and offer will try to put something in the queue. If it can't, it doesn't throw an exception, but it will return false. So you can see if it actually succeeded or not. You also have a timed offer, so that will work if it happens within a certain time. Otherwise, it will return a failure. Similar to that is a transfer queue. Now, transfer queue is slightly different because, first of all, there's no specified capacity. Second of all, when you transfer, you see that the thread is staying with it, even though there's it seems like there's availability in the queue, but the putting threads are synchronous with the put. So the putting thread is not released until we call the take method. Now, if you call take before there's anything on the transfer queue, the takers, you see, from the transfer queue will just wait for something to be available. And you see, once something is available, it will take them. Okay, now we're up to the point I really wanted to get to is the completable future. The completable future is a very robust new construct in Java. It's a great interview question. You can't believe how many people I ask about computable futures on interviews, and they've heard of it but just don't know how to work it. The animations here will describe a lot of the functionality. There's a lot more to implement. It would be nice if people participated, and you could download the GitHub project and actually implement some more functionality, and this will be coming in the future. But the way it works is you have a method called supply async, and that creates a future, and you can supply something that returns a value. So when you call supply async, you could call get, and as soon as that value is available, as soon as that thread is done, it will pull the value out. And now anything that tries to get from that future after that will get that value. You could also do a run async. And what a run async does is it does something. It does some runnable, but it doesn't return anything. So if I try to get from there, it just gets null. There's no value associated with it. It's just kind of a timing thing. Say run this thing and then you're done. Now the nice thing about the completable future is it allows you to compose many completable futures together in various ways. So let's do some supply asyncs. And now let's say I want to create a completable future that will complete when any of its sub-features are done. So the way it works is look at this construct. I say any of, and I pass in a list of completable futures, an array of completable futures. And that means that as soon as any of these completable futures is done, the big completable future, the any of completable future will be done. So let's call get on that. And now let's complete any one completable future. And you see it pulled out value 1. So when I do a get on that, it's always pulling out value 1. Now, what's the all of? So let's do some more of these. And we'll create an all of. Now with all of, where any of completed as soon as any single one of the sub-futures completed, all of requires all of them to complete. So we'll do a get, and we'll see that it can't get anything until all of them have completed. Now you'll notice that it's going to return a null, where the any of returns the value of the first completed future. The all of, there are so many different values, it just returns null. If you need to get a specific value, you'd have to pull it from any one of the futures and perform your operation on those, because you know they're all done. There's also an interesting join method. Now, you notice that the get method has an interrupted exception. So if you're trying to use Java streams, it makes it the code ugly because you have to trap the interrupted exception at each point. The join method will preclude you from having to do the interrupted exception. So it works great when you're doing it inside of a Java stream. The getNow method is kind of interesting because what the getNow method does is why is this going away? GetNow will return a value if the value is not available. So you see it's returning value if absent. But once the value is done, getNow will return the value. So it's kind of an interesting project. You know, there's a project Reactor in Spring that allows you to do all kinds of reactive programming and combining streams and stuff. If you're not using Project Reactor, CompletableFuture gives you a great vehicle for creating reactive applications using these kinds of controls by creating futures and composing them together. Next, there's a completion service. The completion service allows you to submit a callable or a runnable. And the nice thing about it is that you can supply many of them. You can declare how many you want it to be able to create. So in the beginning, we created one with 4. So we were allowing a maximum of runnable, concurrent runnables to be 4. And then we call take on that. And take will return a future, but it won't return the future until the future is ready. And then it calls get on it. So let's complete that. And we see it picked one randomly and it took from there. Now, why is this useful? This is useful because sometimes you have an application where, for example, I had an indexing application. We were indexing some data into a search index. And it didn't matter the order of the search. We just needed to process the data as it came in. So we sent many concurrent threads into the completion service. And then we had one thread pulling the results off of the completion service once they were done and indexing them. So it gives you a great way to submit a lot of results and then have one thread that is actually pulling off of that and processing the end results. Okay, another very common problem that we have is, for example, a hit counter, right? Everybody's implemented some kind of hit counter or counting function. And of course, the famous problem is that if you have 2 threads that are both reading the hit counter and then they are updating the hit counter, well, what happens if let's say the hit counter is up to 100 and 2 threads both say, okay, what's the hit counter now? They both get 100. They both increment the hit counter to 101, and then they both store the result of the hit counter. So now they both record 101, when really there were more than 101, right? There were 102 in that case. So we have to create volatile and synchronization. And so there's a lot of work on our side. What we could use instead is the atomic integer. There's a whole menagerie of atomic components inside the API. But for example, atomic integer allows us to call a get and increment method. So we're saying, you see, all of these threads are coming in at the same time, but it handles all of the concurrency for us. It keeps incrementing. You see 10, 11, 12, you never see a duplicate. So it's handling things in the order they come, and if they come on all together, it is the atomic integer is responsible for maintaining the proper hit counts. There are also compare and set. There's increment and get. So there are many different methods on the atomic integer, and it's really robust. So that's pretty much it for the presentation. One thing is I'd like all the actors to take a bow. So if you're actually working on this application, the way we built it is that each of the sprites that you saw has a sprite instance. So object sprite, thread sprite, runner thread sprite, and each one of these sprites is used. It's dispensed by Spring. So you just ask a Spring Bean and you get these sprites, and it will create it for you. And then the actual application looks at the thread state and it renders it in the proper place. So it'll give you access to that monolith, or it'll keep it outside, or it'll send it running based on the thread state. So there's really very little programming involved in getting the animations to work. The framework does it all for you, and it just leaves the responsibility of coding the actual implementation inside the basic slide. Where we're going from here is, I think the next thing is I'd like to start getting a lot of the project reactor components built into this. As maybe it'll be a separate section, or a separate, maybe even a separate application, because there are really a lot of very robust combination capabilities in Project Reactor. Other than that, get involved, download the Java Concurrent Animated. It's totally been rewritten. There was a version of this that was around for many years, and it was a little difficult to program because the responsibility of the animations was on the programmer. But now the responsibility of the animation is all in the framework, so the programmer just has to code up the application. You can get involved by going to github.com, vgrazi, Java Concurrent Animated Reboot, and please do get involved. Any questions?
Hey, Victor. Yeah, we have a couple of questions over here. So yeah, thank you so much for this wonderful presentation. I mean, this framework where you can actually visualize what's going on. I think that this is great, right? Especially because all of these concepts are really abstract, right? And it's quite hard to grasp and quite hard to understand if you don't have a visual behind it. So I think
and one thing that's really useful, and you're reminding me, is that a lot of times when you're in a concurrency situation where you know you need some kind of construct, what I do is I load up Java Concurrent Animated and I just look through all of them and I kind of get an inspiration of what construct will solve my particular problem.
Yeah, and I remember most of the time when I have to fix those, I always turn to piece and paper and try to basically simulate what's going on over there. But yeah, we have a couple of questions over here, and so let's see what we have. So this is coming from Vinod. He's asking, so with Project Loom coming up, right, and Loom virtual threads on the horizon, how relevant do you think the executors will be?
That's a good question, and I really haven't looked a lot into Loom, so I'm not going to answer that question. But
Okay.
It would be interesting to start trying to animate that though.
Okay. Well, maybe that's a new issue that you have to put there on the GitHub repository.
I'm going to add
it. And this is a more technical question. It's coming from Perez. He's asking, can my stampede lock optimistic read result in a dirty read inconsistency?
It could. That's why you have to do the validate afterwards. But it is faster in the case where you do have rare readers. The locking actually is faster. So if you're in a situation where you need to squeeze out every millisecond of latency, it might be worthwhile to test it out. But it's difficult to find a use case for that because you normally, if you have rare writers, then you might as well use regular read locking instead of optimistic locking.
Yeah, I think we're pretty much done with QA. So I think I'm going to let you go. So Victor, thank you so much for joining us today for this awesome presentation about the concurrency state of things, and especially bringing out this framework to be able to see it visually. So hopefully some people in the audience can have a look into GitHub project and maybe contribute a couple of things. That will be awesome. Well, thank you so much, and let's get ready for a couple of breaks and for the next session. So thank you so much for joining us.
Thank you so much. Thanks for having me.
Yeah, thanks.